Welcome to this explainer. Today, we're diving into the fascinating world of algebraic expressions. If you've ever felt like math is just a bunch of random numbers, well, get ready to change your perspective entirely. We're going to see how math is really just a highly practical, beautifully structured language.
Let's just address the elephant in the room. We have all been there, right? You're cruising along, doing some basic arithmetic, and then bam! The alphabet decides to invade your math homework. It's that totally intimidating moment when letters suddenly start showing up next to your numbers, and it kind of feels like the rules of reality just changed without any warning.
But hey, take a deep breath, look at this calming underwater scene for a second. Just like exploring a vibrant, complex coral reef, you absolutely do not need to panic when you see this new ecosystem of letters and numbers. You just need to dive in and, learn the local vocabulary.
So let's start with the foundation of our new alphabet, the variable. A variable is simply a symbol, usually a letter like X, Y, or W, that represents one or more numbers. Think of it as a completely empty box, just a placeholder waiting for a specific number to be dropped in. It literally gives us the superpower to talk about quantities even when we don't know exactly what they are yet.
And just like a sentence you'd read in a book, every math expression has its own specific parts, and each one plays a very specific grammatical role.
Let's look a bit closer at the structural vocabulary of an expression, like, say, 5x plus 13. We've got our distinct terms, which are the parts being added or subtracted, in this case, the 5x and the 13. Then we have the coefficient. That's the numerical factor of a term that contains a variable. Right here, that's the 5 multiplying our x. And finally, the constant, the number 13 standing confidently all on its own, never changing its value. Honestly, it's exactly like identifying nouns, adjectives, and verbs.
Now this brings us to another brilliant trick of mathematical language, abbreviations. Just look at the clunky way on the left, d times d times d times d. I mean, who actually wants to write all that out over and over? Instead, we use exponents as a grammatical shortcut. That elegant shorthand on the right, d to the fourth power, it says the exact same thing but in a fraction of the space. By simply counting how many times a factor is used, we can quickly condense things down. When h is used as a factor 3 times, it becomes 1.5h to the third power. Or k used 5 times, that just becomes 9k to the fifth. See how we easily translate bulky math into elegant shorthand expressions? It's all about making our communication cleaner and way more efficient.
But just like punctuation completely changes the meaning of a sentence in English, math has its own rigid punctuation rules. The order of operations is the absolute, unbreakable grammar rule that dictates the correct answer. You literally have to follow the steps. Parentheses first, then exponents, then multiplication and division moving from left to right, and finally addition and subtraction from left to right. If you ignore this grammar, your mathematical sentence is going to make absolutely zero sense.
Let's see how this grammar actually works in practice. Watch how we simplify this expression step by step. 4 squared divided by 2 plus 3 times the quantity 9 minus 5. First up, we dive inside the parentheses, changing that 9 minus 5 into a 4. Then, we handle the exponents, turning 4 squared into 16. Next is multiplication and division from left to right, which leaves us with 8 plus 12. And following that precise rhythm right down to the very end, gives us a neat, clean 20.
Okay, so now that we've mastered the vocabulary of variables and the grammar of operations, it's time for the really fun part, translating real-world problems into our new algebraic language. Because this is exactly where you see how incredibly useful this tool is for modeling reality.
Let's look at a super straightforward practical example. Say you babysit for 3 hours and receive $12 total. How do we find your hourly rate? Well, by translating those English words into a simple division expression. $12 divided by 3 hours. We can quickly evaluate the numbers and reveal an hourly wage of $4. Boom! Math just helped us define exactly what our time is worth.
All right, let's level up a bit and look at a slightly more complex goal. Imagine you're diligently saving up for a brand new $125 skateboard. How do we build a mathematical sentence to track this financial goal over time?
So here's the scenario. You already have $45 sitting in the bank, and you plan to save exactly $3 each week. We can easily translate this goal into the algebraic expression 45 plus 3w. You start with a constant, $45, and you add $3 multiplied by every single week that passes, which is represented perfectly by our variable, w.
Now, here is the real power of a variable.
to literally predict the future. Because W is just a placeholder, we can substitute any number of weeks right into it. In 4 weeks, we just substitute 4 for W, do the math, and get $57. In 10 weeks, substituting 10 gives us $75. We can clearly see exactly how our savings evaluate and grow as time marches on.
Which brings us to the ultimate question, right? After 20 long weeks of saving your hard-earned cash, do we finally have enough for that $125 skateboard? Let's consult the math to find out.
Well, unfortunately, evaluating our expression for week 20 shows we only have $105. We are exactly $20 short. Now, while it might be a bit of a bummer for our skateboard dreams right this second, this proves exactly why learning to set up the math helps us accurately plan ahead in real life. We know exactly where we stand today without having to wait 20 weeks just to find out we're short. As we wrap up our dive into this new ecosystem, I want you to remember that algebraic expressions really shouldn't be intimidating. It's just shorthand. It's a beautifully structured language that simply describes the patterns of our physical world. It's a powerful cognitive tool that lets us clearly model reality. In fact, to prove just how long math and language have been playfully tangled up together, I'm going to leave you with this classic poetic riddle from our text to evaluate on your own. As I was going to St. Ives, I met a man with 7 wives. Each wife had 7 sacks. Each sack had 7 cats. Each cat had 7 kits. Kits, cats, sacks, wives. How many were going to St. Ives? With all those wild variables introduced, listen really closely to the grammar of the riddle. How many were actually going? I'll let you translate that one yourself. Thanks for joining me on this explainer, and keep exploring.